I'll begin with a word of prayer. So, dearly Father, we thank you for this day. We thank you, Lord, that we don't have to rely on our own righteousness, that if we accept you, we can have your righteousness instead of our righteousness, which is like filthy rags, Lord. We thank you that you're a good and gracious God, and just guide our work today, Lord. In your name I pray. Amen. All right, so you guys wanted to know about the problem 3.
Yeah, I guess I'm just wondering if you have a path in mind for showing that polynomial is irreducible.
Let's see here. So the question is, why is... So you claim we can look at x cubed minus pi cubed,
Yes.
and that's an element of q adjoin pi, right?
Q adjoin pi cubed.
Q adjoin pi cubed.
Polynomial.
Yeah.
Yes.
And you wish to show x cubed minus pi cubed is irreducible?
Yes.
So what will that do for you?
So that would show that f adjoin pi would be degree 3 over q adjoin pi cubed, and therefore...
Whoa. That would show what?
That, so f is equal to q adjoin pi cubed.
Uh-huh.
And so we're trying to find a basis for f adjoin pi over...
So you say q adjoin pi cubed adjoin pi
Yes, right.
is degree
Degree 3.
3.
So, yeah, if we know that polynomial is irreducible, we know it's degree 3, so then the basis is therefore 1 pi squared.
Right. So the question is how to show that that's irreducible over q adjoin pi cubed.
Because, like, the difficulty is there's some stuff in the book that does similar stuff to this, but the problem is that those are all working on finite dimensional vector spaces, whereas this is infinite dimensional because pi cubed is transcendent, or transcendental.
Yeah, transcendental, right. Let's see here. Well, certainly if you have this, then it follows that the basis for q adjoin pi over q adjoin pi cubed is 1 pi and pi squared.
Yeah.
Yeah.
I mean, that's what I have written so far.
Yeah, I mostly just have a calculation of that directly. Could be that that's what you're supposed to do. I mean, that was my solution.
Just assume it's irreducible and then...
No, I mean, I just look at, what I did was I just looked at let's see here. I looked at f of x in q adjoin pi. All right. So f of x in q adjoin pi is a polynomial whose coefficients are essentially power series in pi, with no notion of convergence, of course, just formal power series in pi. But then you can take each one of those formal power series in pi and you can split it into the 3z plus 1, and 3z plus 2 parts. Regroup those, and then you've got your decomposition. I calculated it directly without reliance on the... Now, there may be a gap in my solution still, and maybe I still face the same thing So what does this look like? It looks like the sum, excuse me, say I equals 1 to n, right? Of ci x to the I, right? But here, ci is equal to the sum bij, pi to the j, j equals 0 to infinity. Because that's what a typical element of q adjoin pi looks like, right? This is what if the If the adjoint element's transcendental, then we don't take finite sums of the powers of the element. We have to allow for infinite sums. They don't have to all be non-zero, but we have to allow for possibly. I mean, it could be that b sub ij is 1 for all ij. That's possible. I mean, that is an element in Q adjoin pi. I mean, there's no notion of convergence in Q adjoin pi. It's what you might call formal power series in pi. It's very big. Well, maybe I'm wrong about that. I got to go back, and I'm telling you, I think that's what we mean by it. But well, what is Q adjoin pi by definition? It's the smallest field, which what? Yeah, pi and the rational numbers.
Yeah, so any element of Q adjoin pi would only involve things that are like, they use a finite, powers of pi up to a finite.
So I think it's just polynomials in pi?
So it would include
Oh, okay, so
all the powers of pi, but any individual element
well,
cannot be different.
that makes me feel better. I think you're right, because what I just said felt wrong.
Yeah.
So we have but this is still a good notation. It's just that we have to add a little fine print, which is that bij not equal to 0, finitely many, many j. Yeah, that yes. I'll try to double check on that later today, just to make sure I'm not. I think you're right, though. I think that's what we must mean by that. Well, here's a different way. I mean, it could be that there's objects built from infinitely many pi, right? There could be numbers built from infinite series of pi's with appropriately chosen coefficients, right?
But then it wouldn't be.
And in principle,
smallest.
yes, in principle, it could even close back to be a field, but it wouldn't be the smallest one, right? Because if you can prove that that's a field, then that's going to be smaller than the ones with convergent series. So.
Yeah, the smallest field just means that you take all the finite combinations. And
Right. So, okay, so yeah, that looks worse than it is, right? It's actually just a nice notation for. But then my point is, this, of course, is the sum over I equals 1 to n, sum over, j equals 0 to infinity of bij pi j, right? X to the I. And, oh yeah, I'm sorry, guys. I don't need to be, I don't know why I'm looking at a polynomial at the moment. That's dumb. Like, I don't need to be looking at a polynomial. I don't know, I'm sorry. This is an unnecessary complication of what I'm trying to explain to you guys. Can I just focus in on the part that matters, which is this? Right. This is not wrong. It's just not the point, right? I mean, let's scrap this for a second here. And there's an X missing here too also. That should have been troubling to you. Let's try this again. So let's just suppose that, constant is an element of Q adjoin pi, right? That means that C is equal to the sum I equals 0 to infinity, right, of C sub I pi to the power I, with finitely many C sub i's non-zero, right? I mean, that's what it means to be in Q adjoin pi. Okay, you doubt? I see doubt.
Oh, well, I just think of it will be quotient by something. I mean, quotient by sum of pi too. But I mean, you have to split
Yeah,
It's
I think
just,
if you want to look at it in terms of quotients, I think we have to think about something like some sort of infinite object built from pi, and then we take the quotient by all possible polynomials in pi, or not polynomials, the quotient by all more than polynomials or something like that. I mean, if you wanted to obtain it as a quotient.
Or do you just mean, no, are you talking about like
I don't think we obtain
pi
this
to
as a
negative
quotient.
powers, like rather than just like summing over all the positive, non-negative powers of pi, we also use the inverses of pi, etc.
Oh, do I need reciprocals of pi as well?
Or can we say something else?
but you have to split it into two cases because if pi is algebraic, then you would just have that sum only because quotient is not much of a meaning.
Yeah.
But if you have pi is not algebraic,
Right.
you would have to quotient that.
If pi is not algebraic,
And,
all right. I'll tell you what. Let me finish this, and then I'm going to look up and try to come back to that because we have obviously not laid the groundwork enough here for that yet. But the point here is, I think this makes sense. Worst case scenario, I have to have the sum minus infinity to infinity, right? If I buy into what you guys are trying to sell me at the moment, right? And you might be right. It's possible. Like I said, I only have my like preliminary solution, I guess you could say. But my point is this sum can be broken into three pieces, right? You can look at the sum I equals to 3k, I equals to 3k plus 1, I equals to 3k plus 2. And in so doing, you'll peel off, pi to the 3ki, pi to the 3k, pi to 3ki, and left over 1 pi or pi squared. And that shows that this number c can be decomposed in terms of the basis 1 pi and pi squared with coefficients in q adjoint pi cubed.
But how does that show that they're linearly independent?
Suppose that they weren't. To suppose that, I guess that just is a question, can you write, so if you take coefficients c1 plus c2 pi plus c3, these are the wrong letters to use, let's say b, b3 pi squared. Yeah, so so suppose that you had a linear dependence. I think you can get a contradiction.
I would assume so, but I would
Yeah.
be able to figure out how to show it. That was my main question.
I don't think so.
Mm.
If pi is algebraic, then you would have that.
But pi is not algebraic. We must strike that from the record. Pi is,
Well, if you have that, then you already, it's straightforward.
so if pi is transcendental, you say it's straightforward.
Yeah. You have that. You can.
You say, okay, so, okay, let me rephrase that. We already know that pi is transcendental over q.
Yeah.
What you're saying is, and I think this is good that you're thinking like this, is we don't already know that pi is transcendental over q adjoint pi cubed.
Right, because it's definitely not, because it's a solution to my one, and it can't be.
Ah,
So it means you don't even need x cubed minus pi cubed. You just argue directly that if b1 plus b2 pi plus b3 pi is times pi squared is equal to 0, then all of them is equal to 0.
Okay, but how do you show that?
Yeah, I'm going to show that. No, if b1.
now here, to be clear for this discussion, we're talking b1, b2, b3 elements of q adjoint pi, right? Cubed.
Pi cubed. Yes.
Or pi.
No, pi cubed.
Pi cubed, okay.
Yeah, so since pi is transcendental, I haven't proved this, but I think that it will be q adjoint with pi
Oh.
cube will be pure fraction of integral domain.
So
When q
it's actually the calculation I'm just showing in reverse, I think. If you plug in that these have the expansions in pi cubed, right? Then you write this out. That gives you a power series in unique powers of pi. But by the transcendence of pi over the rationals, it gives us that all of the coefficients vanish, and hence these in particular vanish. because they're built from linear combinations of those vanishing coefficients.
I gotcha. I think that makes sense.
But I also think that in retrospect, we can see that x cubed minus pi cubed is irreducible over.
How do we, wait, how
Can
do
we
show
see that?
without using this linear independence argument?
I don't know, right offhand. But maybe
It
it's,
seems like-
I bet it's the same argument.
Yeah, but this argument I think works.
All right, just a second here. Let me try to find where the
Definition of the joint.
definition of I'm what I'm interested in is where he discusses the not algebraic but transcendental extensions. Have you guys already concluded there's no useful? I have a hard time believing there's not something insightful in here about that. Am I wrong?
All I know is I only found finite.
So we got 527, 534, 520. $520, maybe where he introduces, I don't know. The definition of, if f is not the root of any non-zero polynomial with coefficients in f, then alpha is said to be transcendental over f. All right, great. 527. I mean, we have things like algebraic extensions. If algebraic extensions are algebraic, yay. Here it tells us that pi is transcendental.
But it just says it's arbitrary.
Indeed, yes, it is. It involves. I mean, last semester I walked in Calculus 2. We actually looked at the proof that E was irrational. That's that's tricky, but not too hard. I mean, yeah, I suppose we could spend a class trying to prove that. We could look it up and we could work on it. Where is this thing here? So the other 534 is in the constructibility section. Here's about squaring the circle is equivalent to determining whether the real number pi is constructible. Yeah. Again, no proof. What I'm really looking, though, is for a more general comment about what it means to be transcendental. Maybe 645, I don't know, we'll see here. Yeah, section 14.9 is on transcendental extensions, inseparable extensions, and infinite Galois groups. So a subset A1 through AN of E is called algebraically independent over F if there's no polynomial in n variables, all right, such that f of A1 through AN is 0. An arbitrary subset of S is called algebraically independent over F if every finite subset of S is algebraically independent. The elements of S are called independent transcendentals over F. A transcendence base of E over F is a maximal subset with respect to inclusion of E, which is algebraically independent over F. Prediction E comma pi as an example. I don't see it. Ooh, matrices. Oh. Oh. Not helpful at the moment. Come on. Man. I had hoped for an example in here or something that I could do.
So, do we know that we can write any arbitrary element of C adjoint pi cubed as a sum from I equals negative infinity to infinity of constants of rational numbers times powers of pi cubed? Is that what it means for it to be the smallest field?
Yeah, I think that's right. I think it has to be the essentially the Laurent Laurent polynomials in pi. Laurent polynomials are like Laurent series. I mean, they're polynomials with positive and negative powers of pi, right? That would make sense because I do need 1 over pi to be in there, and I don't think I can build 1 over pi from a polynomial in pi,
You can't,
right?
Because
Yeah.
it's kind of like what we were doing last semester with all cyclic groups are either like finite.
So yeah. This makes sense. This makes sense because okay. So here's the thing, and it's just a quirk of last semester. We didn't talk about this more, but Q adjoin pi in the sense of a ring. This is up because there is no matter how many times you square pi, you never get like, oh, pi to the millionth plus 1 is equal to pi to the 30th or something. Like that never happens. You can prove that. So pi to different powers are linearly independent, which means that you can think of pi as an indeterminate. There's a natural isomorphism between this and the polynomials with rational coefficients, right? And so the field of fractions of the polynomials with rational coefficients is rational functions in X. Is that the smallest field?
I haven't.
Yeah.
Wait, so if they're isomorphic, is this taking into account the negative powers?
Well, my point is, these are both integral domains,
Right.
so we can do the field of fractions construction, and I think that will produce Q adjoin pi over here. All right, we have some things to think about. I'm going to go on, okay? Curious. Yeah, I sometimes, well, anyway, these things are always a little bit confusing. Yes, as I mentioned to you guys, there's something I'm mourning. Not a person, it's more a program, a system of ideas. I'll tell you later. Let's see here. Where are we? It has nothing to do with the State of Union address. That's purely coincidental, by the way. Just to be clear. All right, so splitting fields. Excuse me. So last time, we essentially looked at, x cubed minus 2, over q, right? And we figured out that the splitting field of this is elegantly written as q adjoin the third root of unity and the square root of minus 3, basically, right? And over this, we have subfields. We have q adjoin the square root of minus 3, and then we've got these guys, right? I called them theta 1, theta 2. Well, let me just write out what they are. Theta, the first one would be the, goodness gracious, what was it? Yeah, that, well, one of the things we learned last time was that this was equal to this, right? As it's written. So that's not what I mean. Right, those in fact are the same field. I mean, the third root of unity, remember, is minus 1 plus the square root of minus 3 over 2. So yeah, I'm supposed to put the cube root of 2 here, positive cube root. So cube root of 2 is one thing. We can do the cube root of 2 times the third root of unity. Or then also q adjoin the cube root of 2 times the third root of unity squared or conjugate. You pick your poison however you want to look at that. These three fields on the right-hand side are what are known as conjugate subfields, I believe, but that's for later. But they're kind of related in some sense, right? Those are just different. Those correspond to the different roots of the polynomial we're splitting, right? this field is somehow attached to the cube root of 2. That's the complex root, cube root of 2, third root of unity, and then the third root of 2, root of unity squared. And then, of course, these are all over what? Down here, you got your rational numbers, right? And the degree of these extensions, well, the adjoint square root of any number not in the remember, with the general example, if we take Q adjoin D, where the square root of D is not in the field, that's a degree 2 extension, right? And then this is a degree 3 extension. I know that because x cubed minus 2 is irreducible over Q, right? And so that's what this is. I mean, this is this is isomorphic to Q adjoin x mod x cubed minus 2, right? And well, this is also those are also degree 3. So let's see here. So ignore these 3's for a second, right? Think about this. So that's degree 2, right? That's degree 3. So what's that say? That says that we have 2 divides the degree of the splitting field. Let me call this thing K so I don't have to write so much. 2 divides the degree of the splitting field K over Q, right? And 3 divides the degree of the splitting field K over Q. By the earlier example that adjoining square root is degree 2, and this by the irreducibility, the fact that cube root of 2 is algebraic over Q. So what's that say? That says that 2 and 3 both divide the degree of K. But we also had the thing I did at the start of last class, right? Which was that x cubed minus 2, that's the splitting field for x cubed minus 2. And we have a general proposition that said the splitting field of a nth order polynomial is at most what? Degree n factorial over the base. So we have that the degree of K adjoining Q is less than or equal to 6. The fact that 2 divides it and 3 divides it forces it to be equal to 6. Once you know it's equal to 6, that also then, of course, forces these two things to what? Either be degree 1, 2, or 3. In fact, I think you could probably give me a separate argument that these have to be degree 3 over Q. How would you do it? How do we know those have to be degree 3 over the rationals? They're subfields. Certainly they're subfields of the splitting field. What are those fields? It's Q adjoin. Yeah, they're all. Oh, that's right. We have a theorem. Perfect. We have a theorem that if we have different roots, right, of a given polynomial, that.
Because they're all solutions to x cubed minus 2.
What's that?
They're all roots of x cubed minus 2.
All roots of x cubed minus 2. Right. So that means that they're isomorphic. Very good. Yeah, we need to remember these things. Otherwise, all of a sudden, it makes really simple questions complicated, right? We have to keep a hold of those results as we go on here. All right. So moving on. So I thought it would be healthy to revisit that since I, quibbled a little bit about whether or not how we know things. And there's no need for that. This is a nice example. Excuse me. X to the fourth, well, he has x to the fourth plus 4 in the book. I'll let you read that. I kind of like x to the fourth minus 1. It's more fun. X to the fourth minus 1 is x squared plus 1, right, times x squared minus 1, which is what? That's x plus I, x minus I, x plus 1, x minus 1. So if I'm thinking about the original polynomial over q, right? What's the splitting field for x to the fourth minus 1 then? It's not split. It's not split over the. It's not split over the rational numbers, right? Because x squared plus 1 is irreducible, and it's not a linear factor, right?
So it's split over the rationals and join on.
Right. How do we know that that's a splitting field? What does it take for something to be the splitting field?
You can generate all the factors from Q to I.
Right, right.
There's no proper subfield that has it, which in this case, obviously, there's because I is the solution is the root of a quadratic polynomial, which is irreducible, therefore there can't be.
Right. So yeah, it has to have all the roots, and we can't take away any of them. Right. So that's why q adjoin like square root of cube root of 2 is not a splitting field for x cubed minus 2 because it's missing two roots. Right. Same for this. Q adjoin the cube root of 2 times the third root of unity is not a splitting field for x cubed minus 2 because, again, it's missing these two other roots. There's no way you can get these two other roots from just one of them. I think if you had both of them, you get it. Pick any two, you can get the third, but yeah, that's not what the question is about. So who cares?
If you have one of the ones on the right, then you can take the other by, you can get a conjugate of it to get the other using the process we talked about on Monday, right?
Yeah, yeah. So the complex conjugation, right? Yeah, complex conjugation goes from here. You're right. That's a good, interesting observation. This is complex conjugation, isn't it?
So does that mean that if we have those two, could we get the third one, or is it just partitioned into the one on the left and the two on the right? Because we can't get the ones on the right from the one on the left because they're complex.
Yeah. I don't know, but we'll come back to this. That thing we just observed actually is a kind of important aspect to Galois theory. Okay, so another example I thought of. So this wasn't actually example 4. This is example 4 tilde. I think this is example 4 tilde tilde because it's also not in the book. But how about x to the fourth plus 1? See this one. So here's how I think about these guys. I think about this being equal to 0, and I just look for the solutions to this in the complexes. All right. And the complex numbers are the algebraic. Well, they're more than the algebraic closure. But well. Anyway, certainly you can view this as a complex equation, and in so doing, you can find the roots. So why not do it if you can do it? I mean, I'm going to do it. So this basic, if x is actually a 0 here, you're looking for x being an element of one of the fourth roots of minus 1. And so the way to do that, actually, that's a set of 4 things. It's the principal square root of minus 1. It's zeta 4 times the principal root of minus 1. It's zeta 4 squared times the root of minus 1. It's zeta 4 cubed times the square root of minus 1, where I'm using square root of minus 1 to be the principal. So square root of minus 1 is by definition, so here we're looking at square root of z, and what that is it's the square root of the modulus of z, all right, times e to the I arg of z divided by 2. This is just the definition of the principal square root in complex analysis. And you might wonder, why am I doing principal square root? And I might wonder that too, because we're looking at fourth roots. Good grief. Ah, today is the worst. Yay. 4. Like, why are you guys confused? Yes, you should be confused. So the fourth root of minus 1, the fourth root of z, the principal fourth root, and you don't divide by 2, you divide by 4. All right, so what is minus 1 in the complex plane? It's here, right? So in terms of the standard angle, that's pi, right? What's the length? So if this is z, what's the modulus of z? It's just length 1, right? And what's the argument, so arg z is pi. Modulus is 1. So what I'm getting at here is that the fourth root of minus 1 is, by usual terms and conditions of complex variable theory, simply e to the I pi over 4, which is also known as the square root of 2 plus I square root of 2 divided by 2. Or we could be lazier and just write that as 1 over the square root of 2 times 1 plus I, if you like that. What's the fourth root of unity? So remember that this third root of unity is exponential of 2 pi I over 3, right? So zeta 4 is exponential of 2 pi I over 4, also known as e to the pi I over 2, also known as I. Because we got cosine of pi over 2, which is 0, sine of pi over 2, which is 1, so the Euler formula, cosine pi over 2 plus I sine pi over 2, really reduces to just I. And of course, I is a solution to x to the fourth plus 1 equal to 0, right? Because, well, x to the fourth equal to 1, rather, because I times I times I times I times I is 1. Okay, so anyway, getting to the point, finally, this we're looking at is really, I think I prefer square root of 2 over 2, 1 plus I, and then square root of 2 over 2, I'm multiplying by I, right? So that's I minus 1. Square root of 2 over 2, multiply by I again, minus 1 minus I. Square root of 2 over 2, minus I plus 1, right? So there you go. Those are actually the roots of this polynomial. Right? You can picture them if you want. So the first one's at pi over 4, and then 90 degrees, then 90 degrees more, then 90 degrees more. Here's those roots. Theta 1, theta 2, theta 3, theta 4. Right? This is not surprising. They have to come in conjugate pairs, right? Because it's a rational polynomial. So it's also a real polynomial. The zeros come in conjugate pairs, as they do here. And the splitting field, right? So splitting field, what is it? What's the splitting field? The lazy description of the. What's the most lazy description of the splitting field? Q. No, lazy, as in like not thinking. Oh, you mean lazy as in like minimally descriptive. That's good. But I was going to say theta 1, theta 2, theta 3, right? It's the field where you have all of the roots of the polynomial. Now you say that's equal to Q adjoin theta 1. Do I agree with you? In other words, it's but can we be lazier still? This is Q adjoin square root 2 over 2 plus I times the square root of 2 over 2, right? I guess I agree with you. Well, How would I get, how would I get theta 2 from that, for example? Right, but conjugation is not a field operation.
Right, but we described how we can get it yesterday, right?
Oh, I did this already?
Or not yesterday, Monday. That's what I thought.
I did? Oh, I thought I didn't do this one yet.
No. We described how to get conjugates.
Oh. Okay, but that's using an automorphism of the complex numbers. I mean, complex conjugation's a field automorphism. But I would argue this much is clear that I don't think that's actually true. That's not enough. Now, if I have theta 1 and theta 2, I think that's enough, because if I have theta 1 and theta 2, I can add them, right? If I add them, I get I root 2. If I subtract them, I get root 2. So I get I and root 2. With I and root 2, I can build all of these. Why not just use I and root 2? I don't think you can get smaller than this.
You can't write it with one element?
Well, indeed, by your homework, this is, I think, unless I'm forgetting a precondition on that homework problem. You know, one of the things we had was if you join root A and root B, you can view that as a simple extension of root A plus root B. I don't think that's entirely obvious, but after you play with it for a half hour, it's just algebra. I mean, everything here is just algebra, right? So that's a, yeah, if I said presented as a simple extension, then yeah, this would be. But anyway, I mean, obviously, how you present the splitting field, there's some ambiguity, right? I mean, I think this is lazy because this is definitely true, right? I don't think you can be wrong writing this, but it's more right to write this, right? Because this gives you a clearer picture of what the splitting field actually looks like. Notice already that Q adjoin I, what's the degree of this? This has what? Over Q. Degree 2, right? That's a lot smaller than it might have been, right? 4 factorial is 24. Actually, degree 2 splits it. This one, what's the degree of this splitting field?
4.
Yeah, I think it's 4. So, oh, I guess we know that it's degree 4, right? Because the
Q adjoin I. Yeah, Q adjoin I is degree 2. Q adjoin square root 2 is degree 2. We know we can't iterate I for 2. Therefore.
so Q adjoin I is 2. And then the question is x squared minus 2 irreducible, right? Over Q adjoin I, right?
Or even easier, we have Q adjoin square root 2 over Q is 2, and then is x squared plus 1 irreducible over Q adjoin square root 2? Yes, trivially.
Okay, so just flip the role of I and 2 around also. Good. Okay. So yeah, that's going to be degree 4 then, because that, yeah. All right. Moving along here, eventually. So the other two examples in this section, I think left, and of course, like I said, the end of the section essentially it traces, well, it gives you the argument for the existence of the algebraic closure, right? This this Uber field in which all polynomials have zeros for a given base field. And it's based by that pretty argument by Artin. But the other example here is on what's called the cyclotomic field, right? Cyclotomic field, which is the splitting field of what? It's the splitting field of x to the n minus 1, right? And as I was just describing, if you look at, if you look at for the zeros of this, in terms of the complex numbers, if we just look at z to the n, minus 1 equals to 0, in other words, z to the n equals to 1, well, that implies that z is an element of the nth roots of unity, which here's the typical notation I use in complex variables, 1 to the n, right? And so that is, by complex analysis, the nth root of 1, the principal nth root of 1, and then zeta n times the principal nth root of 1. But I'll give you a clue here. Principal nth root of 1 is it's the real nth root of 1, which is also 1. So that's 1. So you end up with just the 1, the nth root of unity, the primitive nth root of unity. This is the 3 gum there. 3. Listen to me. So these are the nth roots of unity, and here, of course, zeta n is e to the 2 pi I over n. I think we talked about this some in 421 already, right? This is a model for the cyclic group of order n. This is a generator, right? This is a primitive generator. I think that is the primitive generator in my language. And if you take zeta n to the power k, also generates, 1 to the 1 over n, right? This is a group, right? It's the group of nth roots of unity. That will also generate 1 to the n or 1 over n as a multiplicative subgroup of the complex numbers for what k? Right? We just need that the greatest common divisor of k and n is 1, so relatively prime k. For example, over here, the fourth root of unity, I is the primitive generator. What else is relatively prime to 4? Not 1, not 2, 3, right? I cubed is minus I. So I and minus I are the generators for the fourth roots of unity, for example. And you can either generate the third roots of unity with zeta sub 3 or zeta sub 3 squared. They're both generators, right? For example. So there's that. And he actually has listed, look, we've gotten all the way out to 4. I didn't write zeta 2 as minus 1, but that's not hard, right? You've known that since college algebra. But this one's kind of fun to write. The fifth root of unity is the fifth root, square root of 5 minus 1 divided by 4 plus I, parentheses, square root of 10 plus 2 times the square root of 5 divided by 4. And that's kind of weird, but you know what's weirder? Is that the sixth root of unity is relatively simple. It's just like 1 plus I root 3. That's kind of messed up, isn't it? I don't know. And the eighth root of unity, goodness gracious, the eighth root of unity, man, the eighth root of unity looks like, it's an awful lot like this.
Well, notice he doesn't give the seventh one, so I'm guessing
Oh.
to higher primes, we just get one.
Yeah, right. But anyway, the field Q adjoin, so Q adjoin the nth root of unity, this is the cyclotomic field. And he argues, of course, for n equal to a prime, that the degree, let's say, if this is prime p, the degree of the cyclotomic field over Q is equal to P minus 1. Because the cyclotomic polynomial, which is x to the P minus 1 plus x to the P minus 2 plus dot, 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 dot. Oh, it's plus minus, plus minus, plus minus, plus minus.
I think it's plus because you have x minus p minus 1, x to the p minus 1.
Oh, yeah, you're right, you're right. I'm sorry, I can't read. I was doing something else the other day where they had plus minuses. It was abstract. It's corrupting my mind. Linear, it was linear. Or was it calculus 3? I don't know anymore. Yeah. But anyway, this is the cyclotomic field, in this case of order, generated by, you notice that if you have a p through to unity, you can generate the rest of the zeros, right? Because the rest of the zeros for this are just generated by powers of that. It's the primitive element. It generates the rest of the zeros for your field, so this is a splitting field, right? Now, if p wasn't prime, I'm not sure that that's is a splitting field if p is not prime? Yeah, it's still a splitting field, isn't it? It just maybe it doesn't have this order, right? Like this example right here, the splitting 4 is not prime, right? And is the degree of this 3? No, it's degree 2. So only when it's prime do we get degree p minus 1. When it's not prime, you can have that different zeros in the cyclotomic polynomial are linearly dependent over the rationals. Yeah. All right, well, I will try to yet again finish this section tomorrow. Wait a minute, Friday. And then hopefully we'll be on to the separation, the separable section, which is fun. I will not cover all of the separable section, mostly just like the start of it. He has some more technical results about separability towards the end that I don't, you notice your homework doesn't have much on separable. I mostly want you to learn how to detect repeated roots. So it's the first 3 pages of that section are most important. And I'll try to state the things at the end because for finite fields, there's some really pretty results which are known, but I'm not sure how much we need them depending on. I'm just going to say we'll come back to that stuff as we need it later if I miss something. So Friday I will